Hello, everybody. I would like to represent some solutions of the algebra section for week 4 in the course Maths 1151 at UNSW. I've started in my class, I've started the solution of this, but I haven't proved. I proved only the part A. I would like to also prove the other sections now, and I would like to repeat the proof of the part A. And then you will have the recording whenever you want, whenever you need, you can go back. Here we have a general matrices. You have A matrices and B matrices, and we have only given that AB and BA are both defined. Then we would like to prove these claims one by one. First, let's prove that AB and BA are square matrices. We want to prove that. So what do you mean? What do we mean that the AB and the BA are both defined matrices? So A is let A be in the size of row A, CA. So row A, or RA, is the number of the rows, and CA is the number of the columns. So B is in the size of RB, and CB, RB is the size of the rows, and CB is the size of the column. Then AB is defined means that it is we can multiply this matrix with this matrix. So AB as a multiplications of these two matrices makes sense. We know that by the definition of matrix multiplications, because the rows of the first matrix has to be multiplied with the columns of the second matrix with the dot product. So you need to have number of the columns in the first matrix should be equal to the number of the rows in the second matrix. This is the definition of the matrix multiplication. This is how we do matrix multiplication. As you know, if you have dot products of two vectors, and those vectors have to exactly the same components, they must exist in the same dimension. You may not have a vector in the n-dimensional and multiply with the, or let me simple say that you cannot multiply a vector in the 3-dimensional space with the dot product in the 4-dimensional space. It does not make sense. This is exactly what is happening here. So in order to be able to multiply them, we have this column CA has to be equal to the number of the rows in the second matrix. If that is the case, the multiplication matrix will be on the size RA times CB. So the row of the B matrix was exactly the row of A, and the number of the columns of the matrix AB is exactly the number of the columns on B. In a similar way, BA is defined. I'm just applying what is given to us. It's given to us that AB is defined and BA is defined. BA is defined if the multiplication makes sense. Multiplication makes sense if and only if the number of the columns in the first matrix is equal to the number of the rows in the second matrix, which means CB is equal to RA, then the multiplication will be in the size of RB and CA. Then this from here and here we have this equality. So here we have RA is equal to CB. RA is equal to CB, is this one, right? RA is equal to CB means that this is a square matrix. I'm using this one here. And if we have CA is equal to RB, which means that this matrix is a square matrix because the row of this is equal to the column. And so this is a square matrix and this is a square matrix. That's exactly what we wanted to prove anyway. So let's prove this. Now we assume that AB is equal to BA. Then this is what we want to prove. Let's start from the left-hand side. A minus B plus A plus B. So this is we have a distribution law. So we can assume that A times this, A times that. So we have A times A times B, minus B times A, minus B times B. Now, we assume that AB is equal to BA, so we can interchange this. It means that these are the same. So they just cancel each other. So we have A squared and B squared. Right, these are cancels. We have A squared minus B squared. This is exactly what we wanted to prove. So we are aim is to understand. We can do some algebraic operations with matrices as well, but we need to be careful because not every matrix can be multiply each other. But if you're thinking that you are in the n by n matrices, things are a bit easier. Still, you don't have this in general. Matrix multiplication is not commutative in general. That's what you need to be very careful. Okay. When you're doing the algebraic calculations with the matrices, be careful. Not every matrix are marked. You cannot multiply every matrices. If you are inside the matrix n by n matrices, then you can multiply them, but still they are not commutative. In general, they are not commutative at all. Okay, for this one, this is just that we want to find out an example. We would like to find 2 by 2 matrices such that A minus B, A plus B is different from the A square minus B square. In order to be able to do that, we know that from the previous section, all we need to do is to show that AB is different from it. If I choose the matrix A and matrix B such that they are not commutative each other, they will not be able to satisfy this equality anyway. So for such things, it's always better to choose simple example. So I choose a very simple example with lots of zeros and lots of ones. Lots of zeros is good. So choose A and B and multiply A times B. So this row with this column, you will have 1 here. This row with this column, this is 0 times 1 plus 1 times 0, that is 0. This is 0, 0, so everything will be 0, 0. So A times B is this matrix. And if you multiply B matrix with A, so this row with this column, this position will be 0. And this row with this column, this will be 0. And this row with this column, that will be 0. This row with this column is 1. That is why I have 1 here. As we see, AB is different from BA, so they cannot satisfy this equality because of this part, the part B. I think this is clear. We can move on. Let's prove that A plus B square is equal to A square plus B square plus 2AB if and only if AB is equal to BA. If these matrices are commutative, then this equation, this algebraic equality, will make sense. Let's prove that. Let's start from the left-hand side. A plus B squared is A plus B, A plus B. So I'm applying to distribution law. A times A is A squared. A times B is AB. B times A, BA. B times B is B squared. So here I have AB, BA. If they are commutative, then I can write AB squared is A squared, B squared plus 2AB. That is clear. If this equality exists, then it means that AB squared is equal to A squared plus 2AB plus B squared. Then AB is equal to 2AB. And BA is, I can take this AB on the other side, then I will have BA is equal to AB. I just separate these two in order to be able to prove that. I could do if and only if case from here to here. I just wanted to explain a little bit more. That's all. I have done that. So I've done this question in the class, but let me repeat it. We would like to show AB is equal to AC, and but we know that B is different, and B and C are different matrices. So this implies, with this exercise would imply that we don't have a cancellation law for the matrices. AB is equal to AC, but B and C are different. That's what we would like to practice here. This is a counterexample, which shows that the matrices are not we cannot apply the cancellation law in matrices. So we have A, we have B. Let's multiply these two matrices. This is 3 by 3 matrix. There is the 3 rows. We have 2 columns. So this one and this one. This one and this one will be, so this is equal to 3, this is equal to 3. So it means that we can multiply the matrix A, the matrix B, and the result matrix will be 3 times 2. It's the same thing for C because they are in the same size. So first, it is always a good idea to check the sizes of the matrices before you start multiplying. So as we know, the multiplication means rows and the columns, and with the dot products, row of the first matrix with the column of the second matrix, we are multiplying as a dot product. And this yellow one gives us this position is this one will give me this position, and so on. So this is 1 times that, this is 1, 0 times 2 is 0, 1 times -1 -1. So that's that. From here to here, multiply dot product, 1 times 2 is 2, 0, and this times this is 4. So, and similarly, we will keep going. This times this will be 0, 2, -1, which is this position. This times this will be 0, -2, plus 4, this position. This one, 1, 2, -1, this position. This one times this, 2, -2, 4, which is this position. So this will give us this matrix. If you multiply the matrix A with the C, which is the C matrix, is this one, this row with this column, 1, -2, this one with this column, 1 and 4, 2 and 4, sorry, 2 and 4. This one with this will have 3 -2, this is this position. This times this we will have -2 plus 4, that position. This row with this column we have 2 plus 3 and -4, which is that entry. This row with this column I will have 2 -2 and 8. So that's that position. So here we found AB is equal to AC, but clearly B matrix is not equal to C matrix. So this is a counterexample that the cancellation law is not valid. It does not hold in the matrices. So that's what it is. This statement that B is equal to C is not correct. B is equal to C is not correct. As a correction that needs to be done. AB is equal to AC does not imply B is equal to C. That's what it is. Okay, this one here, this is the n matrix are given. It is just a matrix multiplication. And I is the identity matrix given by 1, 1, 0. This is 3 by 3, and this is the identity matrix in 3 by 3 matrices. And we would like to prove that this is this equality. It is pretty straightforward exercise. We are going to multiply n times n. So this row with this column, it will give us 0. This row with this column, this position will be 0. This one with this column, since this position and this position multiply, we will have 1 here. And this one together with everything, this is in the last row, and this always 0. So this is always 0. and this is always 0, this is always 0. And let's multiply again, n squared times n, then we will obtain 0. So this will be the 0 matrices everywhere. And now by using those matrices, let's have a look what does this equality means. So again, I'm applying to distribution level matrices. I square will be just I. I can multiply I many times. It's an identity matrix. It's always itself. I times minus n, so this is minus n. I times n squared, it's just n squared. Then I have plus n minus n squared, n plus n cubed, which is that one. So n squares will cancel out. Ni is equal to n. So this one will cancel out with this one. I have n cubed here. N cubed is the 0 matrix. And the 0 matrix with another matrix will be just itself. So I plus 0 matrix is the identity matrix. It's pretty straightforward solution. Now I'm going to move on to a new one. So this one here, we have A and B, n by n, as a square matrices with real entries. And A squared is identity, B squared is identity, AB squared is identity. And we would like to prove that AB is equal to BA. Now let's have a look. So A squared is identity and B squared identity. There is no ambiguity. It is clear. But how about this one? What does AB squared means? We know that in general, we don't have the commutativity law in matrices. Let's have a look what it is. AB squared means we are multiplying AB by itself, right? This is AB. AB is the identity, and there's nothing else we can do it. We have to leave it this one as it is. And this is inequality. Now we would like to prove that AB is equal to BA, and now I have many things here, and I know that A squared is identity, B squared is identity. So if I multiply this from the left-hand side by A, I will have A squared, which will give me the identity, right? If I multiply this from the left-hand side with B, I will have B squared, which will give me the identity. So I will be in a good position to discuss something. So I multiply with the left-hand side by A and the right-hand side by B. So here I will have AB. From here I have A squared. From here I have B squared. A squared is identity, B squared is identity. So I have identity, BA identity. So for any matrix, for any D and n by n matrices, identity, by the definition of an identity matrix does not affect at all. So there's an error here. This is D. So multiplication by identity matrix does affect nothing, does not affect at all. So here we have only BA on the left-hand side, and on the right-hand side we have AB, which means that they are commutative. If we have these conditions satisfied, then they are commutative. Okay, let's move on to the next question. This is it is a tricky question, and it is all about the matrix multiplications, looking at a little bit of different perspective. So I have a matrix A, I have a matrix B. So we would like to write down a column vector V such that AB will be the second column of A. Now, this one, first column, this one is second column, this one is third column. If you want to multiply this with the column vector, because see, this multiplication is from the right-hand side. So this one has to be a column vector. So V is a column vector. And I would like to obtain everything in the second column. So V, if I choose V, is 0, 1, 0. It's a very natural way, to choose it, because this multiplication will give me the second column. you can multiply that, but you can see it directly. This times this is -2. This times this is 0. This times this is 2. Multiplications of this matrix with this one will give me the second column because I'm multiplying it from the right-hand side. But this is just a matrix multiplication. Now write down a vector v such that v times b is the third row of b. So again, I multiply the first matrix, I multiply from the rows and the columns. So it's a dot product. So see, this is, I'm multiplying this from the left-hand side. So this should be a row vector anyway. And I want to obtain the third row of the B, which is that one. It means that if I take the vector like 0, 0, 1, which will give me the binary multiplication, just try to imagine with your mind, you will have this vector, and multiply with this matrix, it will give you the last row. That's it. That's just a matrix multiplication, that's all. And write down a column vector V such that AB is the second column of AB. Now this one is a little bit more complicated than the first two, but if I look at the, so I'm looking at the matrix A as a whole, but I am splitting the matrix B in terms of the columns, column B, column 1, column 2, column 3. Like I'm looking at this vector like a C1 vector, C2 vector, C3 vector, column 1 vector, column 2 vector, column 3 vector. I'm just splitting B matrix as 3 vectors. If I multiply A matrix with this matrix, it means that I'm multiplying A with these individual columns, nothing else. Right? So it asks me to write it down the vector V such that AV will be the second column of AB. So this is the matrix AB, and the second column of AB is A times the column B2. So this is just the column of B, second column of B, which is this one, 0, -1, 0, is the answer for this question. And the last one says that to write down a row vector such that VB is the first row of the AB. Now, I am looking at the B as a whole matrix, and I am splitting the matrix A with rows. So the row 1 of A, row 2 of A, row 3 of A. Again, the matrix multiplication is still row 1 times B, row 10 times 2, row 3 times B. It is the same thing. So I'm just splitting the rest AB matrix as row 1 AB, row 2 A2, row 3 AB. So what it's asking me is that what is the V vector, such a V row vector, such that VB is the first row. This is the first row of AB. So row A, 1B. So this is the vector that is in the question. So that is just the first row away, which is 1 minus row 2, 3. The first row of A is 1 minus 2, 3. That's all. Looking at the matrix multiplications in different ways. So this trick can be done. This kind of things you can do it, and it is very powerful. You can multiply matrices with the blocks. You can separate things, and you can do the matrix multiplication with blocks. That's all that I would like to do for this section. Thank you very much for listening.